From a distance, Mars looks like the obvious choice. It has a horizon, a sky, valleys, cliffs, and a day that lasts a little more than 24 hours. You can easily picture humans in that environment. Then, place that image beside something that looks out of this world. The inside of a rotating habitat, a curved floor overhead, sunlight coming through mirrors, fields and homes carried inside a machine with people that call it their new world. One of those places feels natural. The other feels almost impossible. But the human body does not care what a home looks like. It cares about something else. How much gravity is under your feet, how much radiation reaches your tissue, whether the air can stay clean, the water can be reused, and if the whole system can survive when something breaks without rescue from Earth. Mars gives us a real planet, that matters, but it also gives us gravity that is too weak, an atmosphere that is almost useless, and a radiation problem we cannot ignore. A built world starts with a different proposition. It gives up the benefits of standing on a real planet, but it may let us tune the conditions that keep people alive. That is the strange dilemma behind this story. If Mars gives us a solid ground but the wrong environment, could the first serious human colony beyond Earth be a place that never lands anywhere at all? By the end of tonight, my goal is to challenge you to think beyond Mars as the obvious choice, and weigh the benefits and limitations and the size of undertaking to build the machinery required to support entire generations without ever landing on a planet. If you enjoy exploring questions like this with me, subscribing to the channel helps others find them too. Sharing the video helps even more. Let's begin. Mars does not begin as an engineering proposal. It begins as a picture the mind can enter almost at once. You can sketch the red ground, the distant mountains, and the long horizon without knowing a single number about pressure or radiation. If someone says city on Mars, most people can already see streets, domes, cargo ramps, and sunrise on the edge of a base. That matters because many future worlds fail before the imagination can stand inside them. Mars does not have that problem. It arrives preloaded with scene, scale, and direction. It also feels close in the way a planet can feel close even when it is not. The Moon is nearer, but Mars looks less empty. Orbiter maps and rover images have given it weather, seasons, dust, old river channels, and patches of ice, all on a world whose day is not wildly different from Earth's. The result is not familiarity exactly, but kinship. Mars can feel like a harsh cousin rather than a blank rock. That emotional bias runs deep, and it gives a planet with real ground an air of seriousness that a machine in darkness has to work much harder to earn. Then there is the matter of free infrastructure, or what looks free from far away. On Mars, nature already supplied the floor. If you want shielding material, there is regolith all around you. If you want to hide from wind-blown dust or radiation, you can dig. If you need mass for walls, there is mass under your boots. Mars also holds water ice in several regions. That does not solve settlement, but it means a colony there can at least imagine using local material instead of launching every kilogram from Earth. To anyone thinking in freight bills and launch windows, that is a powerful advantage. The cultural story helps too. Mars has been sold as the next frontier for more than a century. Fiction prepared the stage long before serious engineering did. Then real missions arrived. Orbiters mapped the surface, rovers crossed the ground, landers sampled weather and soil. Every successful mission made Mars feel less like a fantasy object and more like a place already entering human experience. It became the planet where our machines have gone often enough that our future selves seem like the next line in the same sentence. None of that is foolish. In some ways, it is exactly how humans decide what counts as reachable. We are drawn to the place that already exists, the place with a sunrise, the place where geology and weather seem ready to meet us halfway. Mars offers a destination story, and destination stories are efficient. They save the mind from asking what a real home actually requires. A planet is there. Therefore, it must be simpler than building the entire environment from scratch. That is the hidden syllogism. There is also a moral comfort in choosing Mars. A planet feels earned. If a settlement stands there, it stands on a world that survived before we arrived and will remain after we leave. The environment may be hostile, but it is not artificial in the ordinary sense. Many people trust that more than a controlled interior. They would rather negotiate with a real landscape than live inside a giant system whose every wall, field, and pressure seal came from human maintenance. Even if the system works, it can feel provisional in a way a planet never does. Yet that whole picture begins from a human instinct that may not be the right one. The body does not care whether a horizon is emotionally satisfying. Bones do not strengthen themselves because a mountain looks noble in the distance. Blood does not regulate itself better because the settlement sits on a real planet instead of inside a rotating structure. Every romantic advantage Mars has in the imagination may turn out to be secondary to conditions people do not feel until they are gone. NASA's work on human health in deep space keeps returning to that point from different angles. Long missions are not threatened by one clean enemy. The risks come bundled. Radiation interacts with isolation. Closed environments interact with mood, maintenance, microbes, and supplies. Distance changes emergency response and medical care. Gravity, or the lack of it, affects muscles, bones, fluids, the heart, and the way the body orients itself. The hidden truth is that a home beyond Earth is not merely a shelter on remote ground. It is a life support argument with walls around it. Once that enters the frame, Mars begins to look less like an obvious answer and more like one contender in a harder contest. Yes, the floor already exists. Yes, there is local mass. Yes, the horizon is real. But those are not the only terms. The deeper question is whether nature already placed people in an environment close enough to what their bodies need, or whether the more realistic path is to build those conditions ourselves, however unnatural that sounds on first hearing. So Mars earns its place at the start of this story. It feels like destiny because it is visible, concrete, and apparently generous in ways a habitat is not. It seems to reduce the amount humans have to invent before they can begin. But that confidence starts to thin as soon as the argument shifts from scenery to physiology. Before asking what we can build on another world, we need to ask what Earth has been quietly doing for us all along. There is another reason Mars keeps returning, and it has almost nothing to do with engineering. A planet gives continuity. The human imagination likes a settlement story that extends exploration into geography and then into ordinary history. In that story, landing becomes a base, the base becomes a town, and the town becomes part of the map. The plot feels legible because it resembles other stories people already know. A rotating world does not offer that comfort. It asks for a civilizational jump in a single image, and many people reject it before they have judged the evidence because it violates the emotional order in which settlement is supposed to happen. That matters downstream because public confidence often shapes what kinds of projects feel serious enough to fund, discuss, or teach. Mars wins this contest almost automatically. Children learn the planets early. Adults have seen rover images for years. Engineers can speak about sites, resources, landings, and transit windows in familiar geographic terms. Even the difficulty of Mars can strengthen the appeal. Hardship on a real planet still reads as adulthood. Hardship inside a giant machine can be mistaken for an elaborate detour. Yet the more the image settles, the more one question keeps pressing at it. If all the visual confidence of Mars depends on features outside the body, what happens when the body becomes the center of the argument? That is where the horizon stops being enough. The planet can still look correct, while the physiology underneath the suits remains uncertain. That reversal matters. Mars feels like the obvious colony first, because it is the easiest place to picture. The harder possibility is that the first durable home might go to the place that was hardest to picture at the beginning, precisely because it was designed around the conditions people usually take for granted. Most of what keeps us alive on Earth is so constant that it disappears from thought. Gravity does not need to announce itself every morning. Air pressure does not need to explain why your blood behaves the way it does. The atmosphere keeps the sky breathable and softens some of the radiation that would otherwise strike the ground. Water cycles through a planetary system so large that in ordinary life we experience it as a background certainty rather than as a machine that must keep running. Even the day-night rhythm that shapes sleep, temperature and routine comes free with the turning of the planet. A house on Earth does not create those conditions, it borrows them. Walls hold out rain and cold, but the deepest parts of the job are already done by the planet itself. That is easy to forget when people talk about colonizing space. They often picture a settlement as architecture moved to a new site, build pressure vessels, grow food, recycle water, add enough power, then scale up. The hidden mistake is that architecture on Earth begins with a full planetary subsidy. Off Earth, more of the subsidy vanishes. The building has to take over jobs that no building on Earth performs by itself. NASA's Human Health Framework for a Mars mission is useful here because it refuses to isolate the problem. It does not treat radiation, isolation, gravity, distance, and closed life support as separate boxes waiting politely in line. It treats them as pressures that overlap. Less gravity changes the body, confinement changes team behavior, distance changes medicine, and closed loops turn contamination and spare parts into permanent concerns. A colony is therefore not one engineering puzzle tackled in sequence. It is several systems pushing on each other at the same time, sometimes in ways that make a tidy fix in one place create strain somewhere else. That is why the word controllable begins to matter more than the word natural. Mars is natural in the ordinary sense. A rotating habitat is not. But natural does not mean suitable. A found environment can still be wrong at key settings. Too little gravity is still too little gravity if the mountains outside the window are real. Too much radiation is still too much radiation if the ground under the base formed by geology rather than by fabrication. The body is not sentimental about authenticity. Seen from that angle, the whole colony question changes shape. It stops asking only which place humans can reach and starts asking which bundle of conditions they can reproduce and sustain with the least damaging compromise. That is a colder question, but it is also a more honest one. A habitat in free space may be able to tune gravity, lighting, layout, and shielding geometry in ways Mars cannot. Mars may offer local material and a ready-made surface in ways a habitat cannot. The argument is therefore less about planet versus machine in the abstract than about fixed conditions versus adjustable ones. That shift matters because it changes where the burden sits. On Mars, some burdens are reduced by the fact that the world already exists. On the habitat side, some burdens are reduced by the fact that the world is deliberately designed. But in both cases, the real settlement begins where the hidden Earth conditions stop being assumed and start being rebuilt. Gravity becomes a design choice or a hard limit. Air becomes a managed chemistry problem. Water becomes a recovery system. Food becomes part of ecological control. Failure becomes a routine design category, not a rare interruption. This is also why casual comparisons often miss the point. A Mars base is sometimes imagined as a tougher version of Antarctica, and a habitat is imagined as a larger space station. Neither picture is wrong enough to dismiss, but both are too small. A true long-term settlement has to function for years under stress. It cannot depend on the fantasy that help is always one launch away. If a loop fails, there must be repair. If a crop fails, there must be backup. If the chosen gravity level proves wrong for human health, the price of that mistake may be measured in decades of compromised bodies. Earth hides how demanding all of this is because it has already integrated the whole package. Gravity, air, pressure, temperature regulation at planetary scale, water cycling, a huge biosphere, a magnetic shield, and an atmosphere thick enough to matter all cooperate before any city is built. Off Earth, a colony has to gather enough of that package back together to become more than a mission. That is why the emotional language of frontier settlement can mislead. It suggests a place where people carry ordinary life into a harsh landscape. In reality, they carry a thin replacement for an entire world. Once you hear the problem that way, gravity moves to the center. It is not the only requirement, but it may be the one people most often wave past because Mars seems to offer a partial version of it. Mars is not weightlessness. That makes it tempting. But the line between some gravity and enough gravity may be where the whole comparison turns. Consider how much ordinary health assumes load. Bones are constantly responding to force. Muscles maintain themselves partly because the body keeps asking them to hold posture, move weight, and recover balance. The heart and blood vessels work within a system shaped by constant downward pull. Take enough of that pull away, and the body begins rewriting its internal expectations. Space medicine has spent decades documenting that rewrite in microgravity. What we do not yet know is how much of the rewrite still happens when gravity returns only halfway or a third of the way. That uncertainty matters because a colony is not a stunt. It is not a 6-month mission with heroic trade-offs. The aspiration behind the word colony includes ordinary life, long work cycles, aging, injury recovery, childhood development, pregnancy, sleep, routine exercise, routine laziness, and the 1,000 habits of a body that is not constantly performing under mission discipline. A settlement that survives only by forcing every resident into the physical vigilance of an astronaut has not yet become a normal place for humans to live. This is also why the environment cannot be reduced to hardware count. A technically successful base can still be a biologically bad home. People can breathe in it, eat in it, and keep the walls sealed while slowly paying health costs that become visible only over time. Earth protects us from making that mistake in ordinary construction because the largest conditions are already right. Off Earth, those conditions have to be chosen, measured, and sometimes guessed at before the long evidence exists. So the body wants more than shelter, it wants a full background, or at least a close enough imitation of one. Every later question grows from that same demand. Which route lets humans rebuild enough of Earth's hidden support without triggering a new failure somewhere else? That question never fully goes away. Mars gives about 38% of Earth's gravity. On first hearing, that sounds almost reassuring. It is not zero. People would walk instead of floating. Objects would still fall. Tools would still have weight. Water would not drift into spheres through a cabin. If you have spent any time looking at astronauts on the International Space Station, Mars can appear close enough to normal that the biological problem seems reduced to a manageable footnote. That intuition is one reason Mars retains its power. We know what microgravity does badly. We have decades of evidence for muscle loss, bone loss, fluid shifts, changes in vision, and the steady need for exercise as a countermeasure. Mars seems to break free from that category. The body would have a floor again. Tasks would not all be adaptations to floating life. The ordinary picture is a person striding through a pressurized base, a little lighter than on Earth, but still recognizably human in posture and movement. It feels like the dangerous part has already been left behind. The trouble is that more than zero is not the same as enough. Enough, a NASA-linked review on partial gravity, makes the problem blunt. It argues that gravity below about 0.4 g may be insufficient to maintain long-term musculoskeletal and cardiopulmonary conditioning. Mars sits almost on that warning line, and just below it. That does not prove disaster. It does not tell us that every person on Mars would become disabled, but it removes the comfort of treating 0.38 g as close enough by default. That closeness is exactly what makes the number unsettling. If Mars offered 0.8 g, the story would be very different. If it offered 0.1 g, the danger would be obvious. Instead, it sits in the ambiguous zone where optimism can survive because the gap is small, while concern survives because the gap may still matter. Near is not the same as safe. A bridge load limit can be missed by a little and still be missed. The body may care about thresholds we do not get to negotiate with. Modern partial gravity research strengthens that caution without giving a neat answer. A recent Science Advances study on partial gravity found that lower gravity levels do not preserve every tissue or function equally. Some outcomes improve at one gravity level, while others need more. In plain terms, the body may not have a single switch that flips from failing to safe as soon as gravity rises above some general floor. Bone, muscle, force production, circulation, and other systems may all respond on different curves. That is awkward for any colony plan that wants one clean sentence. We should be careful here. The data are not a final human verdict. Some of the evidence comes from animal models. Human adaptation over long periods remains uncertain because nobody has lived for years at Mars gravity. That uncertainty has to stay visible. It would be false to say Mars gravity is proven catastrophic. The honest position is narrower. Mars gravity is unresolved in exactly the place where a permanent settlement needs confidence. A mission can survive uncertainty. A colony has to base generations on it. And if the uncertainty cuts against Mars, the planet cannot tune the answer. That is the heart of the problem. You can improve habitat walls on Mars. You can bury those habitats. You can alter schedules, diets, exercise systems, and medical support. But you cannot raise the planet from 0.38 G to 1 G because the settlers would prefer it. Gravity on Mars is not a setting. It is a condition inherited with the destination. That is where artificial gravity enters the story as more than an old science fiction flourish. A rotating habitat offers something Mars cannot offer. It turns gravity into a variable that can be engineered. That does not make the habitat easy. It does not even tell us what the best target would be. But it means a settlement could aim closer to what the body expects, instead of building its future around a planetary compromise that may turn out to be biologically costly. Notice what has changed. The question is no longer whether Mars is dramatic enough to justify settlement. The question is whether it is generous enough in the one area the body may refuse to ignore. The planet that looked like the obvious first home now carries a number that is almost good enough, and maybe not good enough at all. That is a dangerous place for a colony concept to live. If Mars cannot change that number, there is only one way humans can. They have to build gravity instead of finding it. And that sounds simple for about 5 seconds, until the physics of rotation starts to behave like a designer's trap. The number also changes how we should think about risk across time. For a short mission, uncertainty can sometimes be carried as a calculated wager. If the crew returns before the worst long-term effects appear, the mission may still count as a success. Colonization reverses that logic. The whole point is to stay. Every unresolved physiological question becomes heavier because there is no clean endpoint where everyone comes home and medical teams sort out the damage afterward. Mars, therefore, lives in an awkward category. It is better than microgravity in ways that are easy to picture and probably real. But it may still be poor enough to demand aggressive countermeasures forever. Imagine a settlement where every generation has to exercise intensely, not for fitness, but to keep basic structure from sliding. Imagine medical planning built around a gravity level that might always remain a compromise. Those are not arguments that Mars fails. They are arguments that Mars might remain medically conditional even after the habitats, power, and food systems are all working. This is one reason the partial gravity question has stayed so stubborn. Gravity is not something you can test cheaply on Earth for years at a planetary value. Researchers can simulate pieces of the problem. They can rotate animals, study unloading, examine tissue responses, and compare outcomes. But the decisive experiment is also the most difficult one. People living for long periods at a chosen gravity away from Earth. That means settlement plans are forced to look ahead through uncertainty rather than through final proof. The habitat side does not remove uncertainty. It changes where the uncertainty sits. Instead of asking whether 38% of Earth's gravity will be enough, it asks what kind of artificial gravity humans can build and tolerate. That is still a hard question. The difference is that it opens a design space instead of locking the colony into a single planetary answer. Another way to hear the problem is to ask what Mars gravity would do to planning culture. If the gravity question remains open, then almost every settlement decision has to be made under a medical shadow. Habitat layout, work schedules, exercise systems, healthcare capacity, and even crew selection may all be shaped by the fact that the baseline environment is not trusted yet. That is a difficult foundation for a place meant to feel permanent. Even the language people use can become misleading. Saying that Mars has gravity can quietly imply that the gravity issue has been solved because a floor exists and falling objects fall. But a biological baseline is not defined by the presence of a floor alone. It is defined by what years of living on that floor do to tissue, circulation, development, and recovery. That distinction is easy to lose in casual conversation and impossible to lose in a real colony. The reason rotating habitats never fully left serious space settlement thinking is that the basic idea is real. If a structure spins, objects inside it can be pressed outward against the rim. To someone standing on the inner wall, that outward push behaves like a floor beneath the feet. In principle, the trick is clean. Gravity does not have to come from a planet. It can come from motion. A habitat can create weight by turning its own geometry into the source of the feeling. That is the honest strength of the artificial world idea. It is not a fantasy claim that physics forbids. NASA's work on artificial gravity treats rotation as a serious tool. The problem is not whether spin can produce a useful force. The problem is what kind of structure is required before that force becomes comfortable enough for daily life. A machine can create a floor. A home has to create a floor that does not make ordinary movement feel wrong. Small radius designs expose the trap quickly. If the room is tight, you often need faster rotation to get stronger apparent gravity. That brings several penalties at once. Your feet and your head may not feel the same force because they sit at different distances from the center. Turn your body or move your head and strange motion cues appear. The inner ear notices what the architecture is doing. The resulting discomfort is not a minor cosmetic issue if the goal is a place where people will live for years, work normally, sleep normally, and raise children. NASA's Artificial Gravity Handbook gives one useful example. At a radius of about 4 meters, reaching Earth-like gravity at the feet can demand something like 15 revolutions per minute. That is fast enough that the simple cartoon of "just spin the station" breaks apart. The gravity at the head is lower, head turns can feel odd. The environment stops behaving like a quiet imitation of Earth and starts behaving like a clever machine whose trick remains visible in every movement. This is why a rotating gym, a medical centrifuge, a transit countermeasure, and a settlement are different classes of object. A crew might tolerate a harsh spin profile for short exercise sessions or during a limited transit. They do not necessarily want to live inside that profile all day. A colony requires more than function. It requires tolerability. The body is the customer, and the body tends to ask for larger radii and gentler rates than minimalist engineering would prefer. The deeper point is that artificial gravity does not arrive alone. As soon as designers push toward larger structures for comfort, the rest of the project expands with the radius. A bigger ring or cylinder needs more structure. That structure demands more material, and the larger living area then asks for more shielding, more service access, and more maintenance planning. The same physics that makes a habitat attractive is also what begins turning it into a world-sized project. None of this kills the concept. In fact, it is part of what makes the concept serious. Real solutions are often less magical than slogans suggest. Rotation is useful precisely because it lets humans ask a different question from the one Mars forces on them. Instead of accepting a fixed 0.38 g, they can ask what level of gravity and comfort they are able to build. But every degree of freedom comes with design costs that planets do not charge in the same way. There is also an emotional correction here. People often imagine the habitat side as cleaner because the physics seems simple. In the cartoon version, a wheel spins and weight appears. Real bodies are harder to satisfy than that picture suggests. They react to gradients, to head turns, and to the small motion cues that reveal when the trick is still visible at human scale. A spinning settlement has to succeed during ordinary walking, lifting, turning, and rest, not only in a neat diagram viewed from far away. So artificial gravity remains one of the strongest arguments against treating Mars as the inevitable first colony. But it is strong in a hard way, not a soft one. It says humans may be able to build better body conditions than Mars provides. It does not say they can do that with a modest station and a little spin. The floor can be made. Making it feel like a real floor is where the cost begins. Once that cost enters the picture, the habitat stops looking like a device and starts looking like a place large enough to deserve the word world. And the moment it reaches that scale, radiation becomes the next hard test. The habit of speaking about artificial gravity as a yes or no feature can therefore be misleading. A settlement does not simply have artificial gravity or lack it. It has a particular geometry, a particular rate of rotation, a particular gradient from head to foot, and a particular relationship between comfort and engineering practicality. Each of those choices carries downstream effects into structure, power, circulation, interior layout, and maintenance. The floor cannot be detached from the rest of the world that supports it. There is also a cultural difference between a mission countermeasure and a home. Crews on transit vehicles may accept discomfort because the goal is to get somewhere else. Residents in a settlement will judge the environment by a harsher standard. They will judge it the way people judge homes. Can you turn your head normally? Can children play without nausea? Can older people move without constant disorientation? Can work feel routine? If the answer to those questions stays no, the design may still be ingenious and still fail at its deeper purpose. That is why the habitat argument stays strongest when it is stripped of glamour. Rotation is useful because it gives humans a lever over one of the central biological variables. Everything beyond that is cost accounting. How large? How heavy? How stable? How repairable? How resilient? The more plainly those questions are asked, the more the idea sounds less like fantasy and more like an enormous but serious attempt to reconstruct what Earth gives away for free. And reconstruction, if it keeps moving towards something people can actually inhabit, quickly becomes a matter of scale. A little spin may help a trip. A world requires a lot more than a little spin. Designers would also have to think about adaptation itself. A habitat might not simply choose one spin condition forever. It may need ways to bring residents into that environment, to test tolerability, and to respond if different people react differently. A world built around artificial gravity is not only an engineering structure, it is an ongoing experiment in human factors carried out at civilizational scale. That is another reason the phrase artificial gravity can sound more finished than the thing itself. The underlying physics have been understood for a long time, but the lived environment remains unproven at settlement scale. The first community that depends on rotation would be testing in everyday life, whether its chosen balance of size, rate, and comfort can hold up across years rather than a brief mission profile. The real question is no longer whether spin can work in principle. It is whether spun life can become ordinary enough that residents stop feeling as if they are inside a workaround. One of the easiest mistakes in this topic is to lump all spinning structures together. A small centrifuge used as a health countermeasure on a trip is not the same thing as a long-term settlement. A station with one rotating module is not the same thing as a self-sustaining artificial world. They all use the same broad principle, but scale changes the category so much that the shared vocabulary can hide more than it reveals. NASA's old space settlements design study understood that clearly. The point of those large concepts was not simply to demonstrate spin, it was to imagine what would be required for human life on a large scale. Once the settlement becomes a place rather than a device, comfortable gravity, shielding, agriculture, atmosphere management, transport, and maintenance all have to coexist. The structure is no longer a clever answer to one problem. It is a framework that has to hold many problems at once. That is why large habitats keep appearing in serious versions of the idea. Bigger radii allow gentler rotation. Gentler rotation can reduce some of the vestibular and Coriolis penalties that show up in tighter structures. Large interior volumes can also give designers room to separate systems, lay out maintenance pathways, and create environments that do not feel like every wall is part of a cramped machine. In other words, scale is not only spectacle, it is part of the attempt to make artificial gravity livable rather than merely demonstrable. The attraction of that path is obvious once Mars gravity enters the comparison. A built world can aim toward the body's preferred condition instead of accepting a planetary default and hoping it proves good enough. It can seek near-Earth gravity, or at least a level chosen after evidence and caution rather than inherited from a destination. That same design freedom can extend into lighting, thermal control, interior layout, and shielding. A planet asks settlers to adapt themselves to what exists. A habitat allows them, at great expense, to adapt the environment back toward themselves. That is the strongest, honest advantage the habitat side has. The appeal is not romance, but control. If gravity turns out to be the central long-term bottleneck, then a world that can tune gravity may be healthier than one that cannot. The claim has to stay modest. It does not prove that one full Earth gravity is mandatory, and it does not prove that habitats therefore win the whole comparison. It simply explains why the idea remains serious even after the easy science fiction glow is stripped away. But comfort bought by size is comfort bought by burden. As the habitat grows, the shell grows with it, and so does the amount of material that has to be launched, processed, or moved from off-world sources. More interior means more shielding demand, broader circulation systems, larger farms, larger water systems, more inspection, and more places where something can go wrong. The same scale that makes the environment more humane also makes the project more industrial, more expensive, and more dependent on upstream competence. There is a subtle psychological reversal in that. Small spinning habitats often look technically humble. Large ones look extravagant. Yet if the goal is to create a place where people can live without the constant reminder that they are inside a trick, the larger structure may be the more biologically honest design. Humility at the level of hardware can become arrogance at the level of human adaptation. A tiny spinning room may be modest to build and expensive to endure. Mars, of course, avoids this specific geometry problem because the planet already supplies a huge radius. It is an ordinary floor in the bodily sense. The issue is that the ordinary floor is set at the wrong strength. The habitat solves that by turning the floor into a product. Mars solves it by asking people to trust that 38% of Earth's gravity will prove enough. Both routes are uncomfortable in their own way. One is physically crude to the body. The other is industrially huge. That keeps the story balanced, which is exactly where it should be. Large habitats are not a clean escape from Mars. They are a different compromise package. If they are the first serious off-world homes, it will not be because they were easy to imagine. It will be because humans decided the body was important enough to justify the burden of building an environment that behaves more like Earth than Mars does. And even then, comfort under your feet is only one part of the problem. Once people leave Earth for long periods, the next question is not whether a floor feels right. It is how much radiation reaches everything that lives behind the walls. Large scale also changes social possibility. A cramped spinning module can keep people alive. A larger habitat can begin to support separation of functions. Living quarters can be distinct from machinery. Agricultural spaces can be distinct from repair spaces. Noise can be managed instead of tolerated everywhere. Private routine becomes more conceivable. That does not turn engineering into sociology, but it reminds us that a colony has to become more than a life raft if it is meant to persist. The old settlement studies were reaching toward that truth, even when their aesthetics now look dated. They were asking what kind of size is needed before a habitat stops acting like continuous improvisation. That question remains alive because every small structure in space tends to force people into the same volume as their support hardware. A true home asks for some slack, not luxury first. Slack. Enough room that failure, maintenance, work, and rest do not all occupy the same psychological surface. Mars gains from scale in the opposite way. It begins with a vast outside world and lets settlers carve out tiny safe interiors within it. A habitat begins with a total interior and has to build every meter of that interior deliberately. That contrast is powerful. Mars offers unlimited outside that is mostly unusable. A habitat offers limited inside that may be highly usable if it is built well enough. The comparison is almost inside out. So when people say a habitat might become the first real colony before Mars, what they are often groping toward is not a claim about spectacle, it is a claim about where sufficient human normality appears first. A floor that behaves well, space for life to be divided into ordinary zones. Environmental variables tuned toward human tolerance. If that package arrives in free space before Mars can offer it on the ground, then scale will have changed not only the structure of the habitat, but the meaning of the colony itself. There is also a moral cost hidden inside smallness. If the structure is too tight, then the engineering savings may be paid for by the residents through discomfort, monotony, and constant bodily adaptation. Large habitats look expensive because the bill is visible in steel, shielding, and mass. Tiny habitats can look responsible while quietly billing the human nervous system instead. For a temporary mission that may be tolerable. For a colony, it may be the wrong economy. That is why habitat scale should not be judged only by whether engineers can close the design mathematically. It has to be judged by whether the resulting place behaves like somewhere people can inhabit without living in a continuous state of correction. The first artificial world that matters will probably be the one that spends enough on environmental normality that ordinary human life no longer feels like an improvised workaround. Radiation is one of those words that can stay abstract until a number touches it. Mars forces the number into view. NASA's Curiosity rover carried the radiation assessment detector, and what it found on the surface was not a symbolic warning. It was a measurable environment. Surface dose rates on Mars, often discussed in the range of roughly 190 to 260 micrograys per day depending on conditions and modeling choices, are far above what people experience on Earth at the ground. The important point is not to drown in units. The important point is that Mars is not passively safe because it has a sky. That thin atmosphere helps, but not enough to turn the surface into a forgiving place for long-term open living. Mars also lacks the thick atmospheric blanket and global magnetic protection that Earth enjoys. The result is a world where radiation remains part of the settlement equation every day, not only during rare emergencies. This matters because many public pictures of Mars colonization still borrow the visual grammar of frontier life. Red dirt, big windows, open landscapes. Those images carry more confidence than the measured environment earns. Curiosity's data also help with the next question, which is whether local terrain can reduce the burden. The answer is yes, but in a bounded way. Rock, cliffs, caves, lava tubes, and burial under regolith can all provide meaningful shielding. Later analyses using RAD data show that topography changes local dose rates. A habitat tucked behind mass or beneath it can do better than one sitting exposed on open ground. That is real advantage. It means Mars settlers are not condemned to take the full surface environment without modification. But the terrain does not solve the problem by itself. People still have to find the right sites, excavate, build pressure vessels, move material, manage dust, and sustain the same closed living environment they would need anywhere else. A cave is not a colony. Regolith over a roof is not life support. Shielded ground helps only after settlers turn it into an engineered living space. Mars remains a place where shelter is built, maintained, inspected, and repaired. The planet supplies some useful mass. It does not replace the habitat. This is one of the places where the emotional image of Mars changes most sharply under scrutiny. The classic picture is a base on an open plain. The more realistic long-duration picture often looks buried, enclosed, and machine-heavy. Thick walls, covered corridors, excavated volumes, controlled air, limited exposure. In other words, Mars may still end with people living inside artificial environments, Only those environments are pressed into a planet rather than suspended in free space. That does not erase the value of the planet. Local dirt is still valuable dirt. A tunnel in rock is different from lifting the same shielding mass into orbit. Mars gives builders options that a habitat must manufacture at high cost. Yet the psychological effect is important. Once a Mars colony retreats below shielding and inside engineered pressure shells, some of the glamour of natural terrain gives way to the same truth that governs every off-world settlement. Humans are living inside managed systems either way. It also means Mars loses one of its quieter rhetorical advantages. People sometimes speak as if a habitat in free space is necessarily artificial, while Mars is somehow closer to natural living. At the scale that matters for health, both may be artificial. One uses a planet for structure and mass, the other uses a built shell. Both depend on air management, radiation strategy, water recovery, and maintenance discipline. The difference is not natural versus artificial in a pure sense. It is where the wall comes from and what conditions remain adjustable after the wall is built. Once that becomes clear, designed shielding begins to look more powerful on the habitat side, at least in principle. If a settlement is already fully built, then shielding can be placed exactly where people live, rather than wherever geology happens to help. But that elegant idea immediately collides with the hardest question on the habitat side. Where does all that protective mass come from, and how do you move it? The Mars environment also varies in ways that complicate simple storytelling. Surface pressure changes with elevation. Seasonal carbon dioxide cycling changes parts of the atmosphere over the year. Dust influences temperature and visibility. Terrain affects local radiation and possibly logistics. All of that means settlers would not simply choose Mars. They would choose a very specific Mars. Site selection becomes part of survival, and every advantage comes with trade-offs in access, power, excavation difficulty, and travel distance from other useful features. This matters because a planet can feel like a universal answer when it is really a menu of hard local compromises. A base that prioritizes ice access may not get the best terrain for shielding. A site favored for engineering ease may carry other environmental costs. Mars is generous in some categories only if settlers accept tight constraints in others. Again, that does not weaken the case for Mars. It simply makes it more physical and less mythic. And once the settlement is buried enough, shielded enough, and enclosed enough, the distinction between living on Mars and living in a habitat on Mars becomes harder to ignore. People would still be living through walls, loops, filters, and power systems. The planet would remain outside as mass and context, but daily survival would happen in a built world nested inside the larger one. That nested world idea is useful because it sets up the next comparison cleanly. If life on Mars may already depend on artificial interiors, then perhaps the question is not whether artificial worlds are strange. Perhaps the question is whether it is better to place the artificial world inside a hostile planet, or to place it where its own design can do more of the environmental work. Mars also asks settlers to think in layers of dependence. The outside world is hostile. The first barrier is the pressure shell. The next barrier may be regolith, rock, or buried structure. Beyond that sit power systems, thermal control, and air management. The result is that the colony's safety is not one wall thick. It is several protections nested together, each with its own maintenance demand. The open planet remains present, but long life may depend on how well humans manage a deepening stack of artificial defenses. That layered logic changes how arrival itself should be imagined. A flag, a landing, or even a first habitat does not yet mean Mars has become a home. The place begins to feel like a home only after those protective layers become durable enough that people can stop treating every day as temporary exposure inside an emergency shelter. Until then, the planet still functions more as a work site wrapped around a fragile interior. So the honest picture of Mars settlement may be less about standing on the surface and more about learning how to disappear into it safely. Digging, burying, insulating, sealing, and monitoring become the real grammar of long stay. That is not a defeat for the planet, It is simply what the measured environment seems to demand. It is worth pausing on how much that changes the meaning of terrain. People often treat terrain as a gift because it is already there. On Mars, terrain is only a gift after it is converted into shelter value. A cliff has to be placed usefully, a tube has to be reachable and stable, regolith has to be moved. Every advantage comes wrapped in work. The planet provides raw opportunity, not finished safety. An artificial world has one clean advantage over Mars when radiation enters the conversation. In free space, the settlement can decide where its protective mass goes. Instead of scouting for favorable terrain, it can wrap shielding around the places people actually inhabit. Geometry becomes a choice. If you want thicker protection over sleeping areas, agricultural zones, or long-duration living quarters, you can design for that from the start. Mars cannot move its cliffs to where the bedrooms are. A habitat can move the walls because the walls are the habitat. That is a real advantage, and it should be said plainly. A built world does not have to accept the landscape as found. It can treat shielding as part of architecture. In the long run, that could matter a great deal because radiation protection is not only about surviving rare extreme events, it is also about reducing chronic exposure across years and decades. The closer a settlement comes to permanent life, the more persuasive designed shielding becomes. Then the freight bill arrives. Every shield is also material. In free space, a protective wall is not something you discover. It is something you source, move, shape, and keep in place. If the settlement is large enough to support comfortable artificial gravity, then the shielding burden grows with the structure. The very features that make the habitat humane can deepen the mass problem. More volume means more interior to protect. More interior to protect means more protective material. More material means a larger industrial system upstream. This is why the habitat route can be more controllable and more daunting at the same time. It lets humans position shielding intelligently. It does not let them do that cheaply by magic. A careful plan for an orbital habitat may be like a careful plan for a storm shelter before the concrete has been poured. The geometry can be elegant on paper. The logistics may still be severe enough to delay the whole project for decades. We have to be disciplined about what is observed here and what is inferred. The research support is strong for the claim that shielding on Mars remains necessary and that local mass can help. The research support is also strong for the claim that a habitat can, in principle, place shielding more deliberately around the living environment. The next step, however, is a systems inference. For that habitat advantage to matter, humans would need enough off-world industry to gather and maintain a huge amount of material. That is plausible. It is not the same as saying such industry is already practically nearer than what a Mars colony would require. Mars gets its own honest point back at exactly this moment. The planet already stores protective mass below the surface and across the terrain. A settlement can use what is there. The material may be awkward. It may need excavation and processing. It may be tied to specific sites. But it does not need to be lifted into place around an orbital world from nothing. If shielding is measured partly in moved mass, Mars begins the race with a lot of mass already present. So the unfairness splits in different directions. Mars gives you local dirt and rock, but the wrong environment overall. A habitat gives you the chance to tune the environment overall, but demands a larger mass-handling civilization before you get to enjoy that freedom. Neither path is graceful. One borrows from geology, the other borrows from industry. That balance matters because it prevents the habitat argument from drifting into utopian confidence. Designed shielding is a serious advantage. It is not a free win. If anything, it is an example of the larger pattern. Artificial worlds may improve the terms of human life only after humans accept a crushing amount of preparatory work. And shielding is still only one part of the survival picture. Even a perfectly protected habitat is not a home if the loops inside it cannot keep water, air, and waste in a stable cycle year after year. Shielding also changes what the interior of a habitat can become. If enough protective mass surrounds the living volume, then windows may be fewer, light may need to be managed by mirrors or distributed systems, and the whole place begins to act more like a controlled biosphere than like a transparent station. That does not make it bleak. It does change what kind of architecture makes sense. Protection at colony scale may ask people to trade some openness for endurance. Mars makes a similar bargain in another form. A buried Martian base might surrender the dramatic skyline people dream about in exchange for survivable exposure levels. In both settings, mature settlement may look less cinematic than the early posters promised. Long life is often less beautiful in the simple visual sense than short visits. You keep the body safe first and let grandeur come later if it can. That reminder is useful because it keeps the story from collapsing into aesthetics. A person can prefer the sight of a Martian valley. Another can prefer the intellectual beauty of a carefully designed cylinder. Neither preference answers the settlement question. The answer will be shaped by how much protective environment humans can sustain around themselves, and for how long, before the whole system becomes too expensive or too fragile to continue. So shielding becomes a wall in two senses. It is the literal barrier that makes life possible. It is also the conceptual wall many easy arguments run into. Every solution that sounds clean becomes heavy. Every heavy solution demands a broader industrial and maintenance world behind it. That is why the loops inside the wall matter so much. The wall only buys time if the life support within it is trustworthy. The form of shielding matters too. Loose regolith, water, structural material, storage mass, and specialized protective layers do not all behave the same way in an engineering plan. The point here is not to claim one perfect recipe. It is to notice that a habitat has more freedom to integrate shielding with everything else it carries. Tanks, stores, walls, and agricultural volumes might all play roles in the broader protective arrangement if the design is thoughtful enough. Mars has its own version of that integration. The same soil used for berms or burial may also shape roads, construction plans, and thermal behavior. In both settings, shielding stops being a single add-on and becomes part of the broader architecture. That is useful because it reminds us that settlement design is never modular for long. The major survival demands begin merging into one another, and once survival demands merge, so do the costs of getting them wrong. A poor shielding choice can affect architecture, maintenance access, psychological openness, and logistics all at once. That is another reason the argument must stay grounded. Clever arrangements may exist, but they still live inside the older reality that every protective gain has to be earned with mass, planning, and sustained care. That may be the clearest place where built worlds and planets mirror one another. Mars asks humans to turn raw geology into protection. Habitats ask humans to turn raw material supply into protection. In both cases, shielding is not an accessory. It is one of the main proofs that a settlement has moved beyond expedition thinking and into the slower logic of permanence. Water recycling is one of the most encouraging facts in the whole settlement conversation because it proves something important. Closed-loop life support is not an empty slogan. On the International Space Station, NASA has pushed water recovery close to 98%. That means the broad idea of reclaiming moisture, urine, and wastewater until the system keeps most of the loop alive is already part of real human spaceflight. The lesson is not that colonies are solved. The lesson is that deep recycling is no longer speculative in the weak sense. That matters because off-world settlement without strong water recovery is hard to take seriously. You can launch emergency reserves for missions. You cannot build a durable community on constant wastefulness. Water is heavy. It is also woven into every other system. Drinking, hygiene, food preparation, cooling, plant growth, waste processing, and atmosphere management all touch it. A high recovery percentage means engineers have already learned how to turn one of the oldest necessities of life into a disciplined technical loop. But percentages hide the part that colonies care about most. A recovery system does not only need to work, it needs to keep working. A station can sometimes tolerate a level of maintenance burden that a settlement would find exhausting over long spans. Filters clog, sensors drift, contaminants appear, spare parts wear out, crew time disappears into prevention and repair. A colony cannot celebrate a recovery milestone once and move on. It has to hold that performance under routine stress while the rest of life continues. This is where reliability becomes the hidden second half of loop closure. Suppose a system reaches excellent recovery under watched conditions, with resupply, mission control, and a finite crew rotation. That is real progress. It still leaves open the question of how the same logic behaves during years of use, during cascading subsystem faults, during crop anomalies, during changes in crew size, or when replacement hardware arrives late. A good colony system is not the one that can post a strong number. It is the one that can survive ordinary ugliness. Mars does not escape that burden. That is an important correction because the public picture can easily make it sound as if a planet somehow reduces life support to a background issue. It does not. A buried Martian base will still need water processors, storage, piping, leak control, maintenance, and contingency planning. Local ice may help at the input side. That is meaningful. It does not remove the need for high-functioning internal loops. Water on Mars still has to be recovered, cleaned, moved, and kept in circulation. In that sense, the water story begins to level the emotional contrast between planets and habitats. Both become machine ecologies. Both need systems that can keep a vital substance moving through a closed environment with very little margin for waste. The question is no longer who gets to avoid water engineering. Nobody does. The question is whose broader environment makes the whole package easier to sustain. This is also where the conversation becomes more adult. Space settlement is often imagined through dramatic first moments. First landing, first construction, first crop, first child. But long-duration survival lives in repeated competence. A settlement does not become serious when it proves it can recycle water on a good day. It becomes serious when the loop keeps running through boring months, minor contamination events, deferred maintenance, crew fatigue, and all the little insults that make real systems reveal themselves. So water recovery is a hopeful fact and a warning at the same time. It shows that humans already know how to close one important loop surprisingly well. It also shows why every optimistic phrase about self-sufficiency needs to be translated back into labor, reliability, and repair. A home in space is not impressive because it can run a cycle. It is impressive because it can keep that cycle trustworthy. And once the water story is told honestly, the next weakness becomes easier to hear. Breathing is not one machine either. The sky inside a colony has to be manufactured constantly. Water is also the clearest example of why percentages can seduce planners into the wrong emotion. A recovery system operating at 98% can sound almost complete, as if the problem has shrunk to a small bookkeeping loss. But colonies do not experience the missing 2% as a statistic. They experience it as logistics, buffer reserves, leakage, contamination events, and the constant need to keep the best day from sliding into a merely acceptable one. High closure is wonderful. It is not the same thing as carefree closure. On the station, crews live inside an environment where every liter is watched closely and every anomaly is treated as mission relevant. A colony would need the same discipline while also trying to feel like a place where ordinary life can happen. That tension is easy to underestimate. The more normal the settlement wants daily life to feel, the more invisible the maintenance work has to become. But invisible work still has to be done. Somewhere behind the walls, valves, processors, heaters, sensors, and filters still need attention. The same logic shapes emergency thinking. When a water loop fails on Earth, cities can often draw from huge external systems, neighboring regions, or old reserves embedded in a large infrastructure network. A remote settlement has a much thinner margin. It lives closer to its own numbers. That makes redundancy, storage, repair access, and contamination control part of the water story from the start, not additions afterward. So water loops teach a discipline that applies to every other subsystem too. Real progress deserves full credit, but real progress has to be translated into duration. Can it survive neglect? Can it survive fatigue? Can it survive a sequence of minor faults instead of one dramatic breakdown? A home beyond Earth begins to deserve the word home only when the answer starts moving toward yes. One more difficulty is that water systems interact with almost everything else. If agriculture expands, water demand shifts. If crew size changes, so does recovery load. If thermal systems are redesigned, condensation behavior can change. A loop that seems stable in one operating regime may behave differently in another. Colonies, therefore, need not only hardware, but an operational culture capable of noticing and responding to slow drift before it becomes crisis. That operational culture may sound less dramatic than rockets and habitats, but it could be the real backbone of settlement. People will have to become good at living with numbers, filters, maintenance intervals, and small warning signs, without turning daily life into panic. The first durable off-world homes may belong to the societies that learn how to normalize that discipline without letting it consume the whole meaning of living there. In that sense, water loops are a rehearsal for civilization beyond Earth. They ask whether humans can sustain an engineered commons when scarcity and failure remain close. That is a hard question on any world. It becomes harder when every kilogram and every litre live under the sign of distance. A settlement that cannot normalize this kind of stewardship will always remain closer to a mission than a home. The pipework may be hidden and the recycling hardware may be elegant, but life there would still depend on constant vigilance that never matures into routine. Routine is the quiet prize. Once a colony can protect its water loop through ordinary competence instead of extraordinary attention, it starts to resemble a place where history can accumulate. That sort of reliability would shape school schedules, hospital planning, food reserves, and the simple confidence that tomorrow can look much like today. If water recovery gives the settlement story some confidence, air closure gives it caution. NASA's work on oxygen recovery shows that the loop is not closed as deeply as the water loop. On current station-scale systems, recovery of oxygen from metabolic carbon dioxide has been partial, around half in broad terms, with development work pushing higher. The exact percentages matter less than the shape of the lesson. The atmosphere problem is not solved to the same degree as the water problem. That difference matters because people attempted to treat air as the easy part. Tanks, scrubbers, and filters sound more manageable than agriculture or shielding. But in a closed settlement, air becomes a non-stop industrial process. Carbon dioxide has to be removed, oxygen has to be regenerated or replaced. Trace contaminants have to be watched, leaks have to be found, sensors have to stay honest. Hardware has to survive without quietly drifting into failure. The environment that feels most invisible in daily life becomes one of the most active engineered loops in the system. The best analogy is not a storage room full of breathable reserves. It is a small atmosphere factory that never gets a day off. If one part of the chain weakens, the burden shifts somewhere else. If carbon dioxide removal slows, the problem arrives in the lungs and bloodstream of the crew. If sensors drift, the settlement can misread the state of its own sky. If seals degrade, the whole budget changes. Air inside a colony is not a passive possession. It is a living balance maintained by chemistry, hardware, labor, and vigilance. This is why strong water recovery should never be mistaken for general loop maturity. Different loops mature at different rates because they depend on different combinations of physical processing, chemical conversion, biology, and maintenance. A colony cannot take comfort from the strongest number in one subsystem and spend it across all the others. The weakness of one loop can still define the character of the whole settlement. Mars and free space habitats end up sharing this burden almost completely. A planet does not give you a breathable sky. It gives you a hostile outside atmosphere and the same need for controlled air inside. The pressure vessel may sit under regolith rather than inside a rotating shell, but the people within it still rely on active atmospheric management. Their breathing still depends on hardware. Their safety still depends on the system balancing itself hour by hour. That is a useful moment in the comparison because it prevents drift into subsystem trivia. The documentary line remains the same. Neither route escapes life support. Neither route becomes natural in the sense people often mean. The real difference lies in what each environment lets you control around the life support system. Mars fixes gravity low and radiation high but reduces some construction burdens with local terrain. A habitat lets you tune gravity and shielding geometry, but makes the settlement itself more like a giant integrated machine. The atmosphere problem also teaches something about scale. A base for a short mission can treat some of these loops as burdens carried for a time. A colony treats them as the condition of life itself. That means every incomplete percentage, every maintenance burden, every unresolved efficiency matters more, as soon as the community is meant to endure and grow. A mission can ration discomfort. A colony has to normalize survival. For all those reasons, air closure stays one of the clearest signs that off-world settlement has not yet crossed from brave engineering into mature ecology. The walls may stand, the water may recycle well, but the sky inside still has to be made and remade by machines that are not yet finished proving themselves at the scale a true colony would demand. And once that becomes clear, food stops looking like a nice addition to settlement culture. It becomes part of the same life support argument. There is a reason air problems feel more intimate than many other engineering failures. People can imagine eating stored food for a while. They can imagine rationing water in an emergency. Bad air collapses those stories quickly because it enters the body with every breath. That is why atmospheric control has a different emotional weight. It is not only another subsystem, it is the settlement's continuous agreement with human metabolism. That agreement has to hold through ordinary variation too. Crew size changes, activity changes, temperature changes. Agricultural systems can alter humidity and gas balance. Leaks can be tiny and cumulative. A colony atmosphere therefore behaves less like a tank and more like a managed chemical climate. Small drifts matter because they do not stay small forever when the whole world is enclosed. This is one reason long-duration settlement may remain closer to industrial operation than many popular images admit. People often picture the emotional test of a colony as loneliness or distance. Those are real pressures, yet there is also a quieter psychological pressure in knowing that the sky above you is maintained by active systems around the clock. Trust in the settlement is partly trust that an invisible factory is doing its work correctly while everyone sleeps. Mars does not reduce that pressure enough to change its nature. Free space does not reduce it either. Both routes must earn breathable normality through the same kind of sustained technical competence. Once that is admitted, the colony question looks less like a triumph of arrival and more like a triumph of maintenance. Because atmosphere is so intimate, it also shapes trust. Residents may never see the whole system, but they will live by faith in it. Faith here does not mean blind belief. It means confidence built through maintenance, measurement, and years of systems behaving as promised. A colony with shaky atmospheric reliability would struggle to feel psychologically settled, even if every other part looked impressive. That in turn suggests that atmospheric competence may become one of the quiet dividing lines between frontier presence and real habitation. A frontier post can tolerate some sense of temporary strain. A home cannot. People eventually need to forget, at least for hours at a time, that the air above them is being actively manufactured. When that forgetting becomes possible, settlement has crossed a deeper threshold. Until then, every breath remains part of the engineering story. That is not melodrama. It is the plain consequence of building a world in places where the outside environment cannot be trusted to do even the oldest work of a sky. This also means atmospheric stability has moral weight. Future residents, including children if settlement ever reaches that point, would inherit a background they did not choose. The adults who build that world are therefore making a promise with every scrubber, seal and recovery system. They are promising that the manufactured sky will stay dependable enough to deserve trust. That promise is easy to say and very hard to keep. And because atmospheric control touches every resident equally, it can become one of the clearest tests of whether a settlement has truly become civil rather than merely operational. A well-run atmosphere is shared trust made physical. Nobody can opt out of it. Nobody can privately compensate for it. The community either keeps the common sky stable or lives under the constant reminder that stability is provisional. That may prove to be one of the deepest social pressures in any enclosed world. For a colony, then, breathable air is not only chemistry, it is continuity. When continuity holds, people gain the freedom to think about work, family, study, and time. When continuity feels fragile, every larger dream rests on a thin foundation. A field inside a space habitat is one of the most seductive images in future settlement art. Green leaves under curved windows, sunlight reflected in through mirrors, a walking path beside crops. The danger of that image is that it can make agriculture seem decorative. Fresh food, beauty, morale, all true perhaps. But NASA's work on crop systems and plant growth points toward a deeper role. Plants can contribute food, yes, but also atmospheric exchange, water processing, humidity management, and waste integration. Farming in a settlement is not a lifestyle choice first. It is a systems choice. That is why official work on space agriculture matters. It keeps the subject grounded. Plants in current spaceflight settings are still largely research systems, not the foundation of a colony's calorie supply. That boundary is important. We should not look at plant experiments on station and pretend a self-feeding orbital city is one step away. Yet those experiments do show that biology belongs in the conversation, because physical closure alone does not do every job elegantly. ESA's Melissa project pushes the same lesson from another direction. If you want a deeper loop, biology enters the design whether you are ready for it or not. Waste becomes feedstock. Microbes become partners and threats. Lighting becomes a life support bill. Humidity becomes both resource and complication. Crop cycles interact with water cycles. Biological systems can help a settlement become more world-like. They can also make the whole thing less predictable than a purely mechanical dream would prefer. That is the real turn here. The more serious the colony becomes, the less it can remain only a machine. A true long-duration settlement may need to become a managed ecology. That phrase should sound heavy because it is. Ecologies are not panels you bolt on. They are interacting systems with delayed consequences, contamination pathways, sensitivity to imbalance, and labor demands that do not disappear simply because the design looks orderly in cross-section. Mars and habitats face this in slightly different forms. On Mars, local conditions may limit what kinds of agricultural volumes are practical, how shielding and lighting are arranged, and how tightly habitats stay enclosed. In a large habitat, the appeal is that agriculture can be built into the broader environmental design from the start. In both cases, though, the issue is the same. Food production changes the atmosphere, water use, waste flow, heat balance, and microbial life of the settlement. It is never just about salad. This is where the built world concept begins to feel more convincing and more frightening at once. More convincing because a large habitat can begin to imitate Earth by combining physical infrastructure with living systems. More frightening because that imitation has to be maintained. An artificial world is not merely a shell with spinning gravity and thick walls. It may be a coupled machine and ecosystem that has to stay stable across years of human error, biological variation, disease control, and equipment fatigue. There is also an honest limit to how much early settlements can demand from agriculture. A frontier habitat, whether in free space or on Mars, may depend heavily on stored food and imported nutrients for a long time. That is not failure, it is realism. The fantasy to avoid is the visual shortcut where the presence of green life means the deeper settlement question has been answered. Greenery may instead signal that the question has become harder, because biology has joined the list of things that must be kept in balance. If there is a hopeful side, it is this. Agriculture reminds us that colonies are not only about resisting death, they are about rebuilding conditions of life with some richness and resilience. The problem is that richer systems are rarely simpler systems. The closer an artificial world comes to behaving like Earth, the more of Earth it has to recreate in controlled form. And once the settlement is both machine and ecology, another hidden comparison comes forward. A place that must constantly repair pumps, seals, filters, lighting, crops, and pressure systems is not only a story about design, it is a story about what can be fixed when things go wrong. Food also brings time into the picture in a way mechanical loops do not. Machines can often be turned on, turned off, repaired, or bypassed quickly. Crops live on slower clocks. They have growth cycles, sensitivity to disease, sensitivity to lighting patterns, nutrient demands, and weak points that may only reveal themselves after days or weeks. A settlement that leans on biology is not only managing things, it is managing timing. That deepens the challenge because some mistakes can no longer be fixed in an afternoon. Biology also changes labor. A valve does not care whether someone finds the work meaningful. A farm can become part of morale, routine, sensory relief, and social life while still remaining a technical burden. That double role can help a settlement feel more human. It can also hide how much expertise and daily attention the system really consumes. Pleasant surroundings do not reduce the seriousness of the loop that keeps them alive. There is an interesting asymmetry here between Mars and a large habitat. Mars can offer local day-night cycles and perhaps easier psychological contact with the surrounding world, even if people remain mostly indoors. A habitat can offer lighting and climate on purpose, but every one of those choices has to be supplied and maintained. One route inherits cycles from a planet. The other manufactures cycles because they are useful to bodies and crops. Again, the comparison is not easy versus hard. It is given structure versus chosen structure. That is why agriculture belongs in the center of this documentary rather than at the edges. It exposes the deepest truth of the whole topic. A serious settlement may need to become partly alive in its operations. The first artificial world, worthy of the name, may not only spin like a machine, it may breathe and recycle in ways that make it feel, cautiously, like a managed little planet. Food also carries cultural consequences. A settlement that grows part of what it eats is doing more than reducing shipments. It is establishing rhythms of season, labor, taste, smell, and waiting. That may matter for morale as much as for metabolism. Yet those human gains come attached to technical demands. Lighting must be stable, disease must be controlled, nutrients must cycle, waste must be processed cleanly. The warmth of cultivation sits on top of a very strict substrate. That strictness is easy to miss because plants make a space feel less mechanical. Leaves soften an interior. Green breaks up hardware. Moisture, smell, and growth make the place feel inhabited rather than merely occupied. Those are real benefits. They should not hide the reality that agriculture at colony scale may be one of the hardest parts of the whole project, precisely because it blends emotional meaning with biological fragility. So when we picture farms inside an artificial world, the best mental image may not be pastoral abundance. It may be disciplined abundance, life thriving because the settlement has learned how to support it without losing control of the loops that keep both plants and people alive. That may be why space agriculture has such symbolic power. It looks like a sign that life has finally taken root. The better way to read it is narrower and more demanding. It is a sign that the settlement is trying to move part of its metabolism inside its own walls. If that succeeds, the place becomes more than a protected camp. If it fails, the failure reaches deep into food, mood, and environmental balance at once. Repair is one of the least glamorous questions in space settlement, which is exactly why it matters. A colony does not prove itself by working once. It proves itself by surviving routine failure. Pumps fail, seals age, filters clog, bearings wear, sensors drift, panels crack, water lines foul. Crop systems get contaminated. If the chosen environment turns every repair into a high-risk operation, then the settlement's elegance on paper means less than people hoped. Mars introduces one set of repair burdens immediately. Dust is the obvious symbol, but it stands in for more than dirt on surfaces. Fine abrasive material gets into joints, seals and interfaces. Partial gravity changes movement and handling but does not remove awkwardness. Distance from Earth turns spare parts and expert intervention into strategic issues rather than convenience issues. Any system that must be serviced outdoors does so in a hostile environment with suits, isolation and delay folded into the job. The planet gives you a floor. It does not give you an easy workshop. Even indoor repair on Mars carries the logic of a remote frontier. Habitats may be buried, volumes may be tight, access routes may be limited by shielding design. Emergency response may depend on a small team under stress with few replacements close at hand. A dust-touched mechanical problem can become a life support problem if it propagates through the wrong chain. None of that makes Mars impossible. It does mean the romance of planetary settlement often underestimates how punishing ordinary maintenance could become. A built world in orbit can claim a different possible advantage. Because the environment is fully designed, some systems can be laid out for access from the start. Modules can be arranged with replacement in mind. Pumps, conduits, atmosphere hardware, and agricultural systems can be planned around maintenance corridors rather than squeezed into a geology chosen by chance. In principle, a habitat can decide that repairability is one of its founding design rules, instead of something adapted later. That advantage has to be kept modest. Maintenance in orbit is not easy. Free space structures still face vacuum, radiation, fatigue, and the danger of failures that threaten the whole settlement. Some external repairs could be terrifying. Large, rotating systems add their own complications. But a habitat at least allows designers to ask from the beginning how a person is supposed to reach, isolate, replace, or bypass a failing part. That question may be harder to answer elegantly in a buried Martian environment assembled under harsher local constraints. What repair really does is stop ideological arguments cold. A person loyal to Mars can say a planet feels like the proper frontier. A person loyal to habitats can say tunable gravity makes the difference. But when a pump fails at 2 a.m, the meaningful question is simpler. Which environment lets the crew get to the problem, isolate it, and recover without turning one bad component into a larger breakdown? That is the level where settlement ideas become adult. Once something has actually broken, the grand story gives way to a simpler question about serviceability and recovery. A built world may score better if it was designed around maintainability, modular replacement, and internal access. Mars may score better where local material and passive terrain provide buffers a habitat lacks. The answer will not be universal. What matters is that repair reveals what each route is really asking people to live with after the speeches are over. It also reveals why the habitat's greatest weakness is not artificiality in the abstract, it is concentration. When enough of the world is engineered together, many failures stop being local annoyances and start threatening the same enclosed system. That is where the next pressure enters. Repair also reveals what kind of knowledge a colony needs to carry within itself. On Earth, difficult problems can often be escalated outward to specialists, supply chains, and manufacturing networks that feel almost infinite from the point of view of one building. A distant settlement cannot rely on that reflex in the same way. It needs diagnostic skill, fabrication skill, spare inventory discipline, and procedural calm inside the habitat itself. That raises the standard for what a self-respecting colony is. Mars makes that burden visible through delay and contamination. Parts may take months to replace. Outdoor work may be constrained by dust, cold, and suit operations. A fault that would be annoying on Earth can become strategic when the next shipment is far away and the environment around the broken hardware is itself hostile. A planet provides material, but it also imposes penalties every time the crew has to leave the safe interior to deal with its machinery. A designed habitat can try to answer that by arranging systems in layers. High-value components can be reached from internal service spaces. Failures can be isolated by compartment. Redundant loops can keep one section alive while another is repaired. None of that removes danger, but it changes whether danger arrives as outside exposure, internal access difficulty, or broad system coupling. The details matter because different repair cultures may grow out of them. Seen this way, repairability becomes a form of honesty. A serious settlement does not merely ask what can be built, it asks what can be reached, diagnosed, replaced, and trusted again after something goes wrong. The route that answers those questions better may have an advantage deeper than public imagination usually notices. Repair culture also shapes politics inside a settlement. Who has authority to shut systems down? Who understands the diagnostics? How much redundancy justifies delay? How much inventory is kept versus fabricated locally? Those questions may sound administrative, but they decide whether a colony reacts to failure with calm or confusion. Long-duration survival may depend as much on competent institutions as on clever hardware. That is another place where nearer habitats may gain an early advantage, not because their problems are small, but because mistakes can be audited more quickly, procedures revised faster, and training pipelines reinforced with closer support from Earth. A Mars settlement may eventually develop the same competence. It simply has less room for casual error while it is still learning. So repair is more than fixing broken things. It is the practical school in which a settlement learns whether it is becoming a real society or only a remote installation waiting for the next shipment. The first artificial world that matters may be the first one whose people can keep their own world working without turning every fault into a referendum on survival. In that sense, maintenance may be the unromantic measure of whether a frontier can become a home. Exploration celebrates arrival, but settlement rewards the people who can keep pumps running, seals tight, inventories honest, and procedures calm after the novelty has worn away. The first environment that supports that kind of durable competence may deserve more attention than the environment with the strongest mythology. It is hard to build continuity far from Earth, and it may be even harder to make continuity boring. Yet boring is exactly what a lasting home eventually needs. Once repairs become ordinary instead of heroic, a settlement has crossed a line no speech can fake, because people can finally plan around the place instead of merely surviving inside it. There is a practical lesson in that for the Mars versus habitat question. The first environment to support durable habitation may not be the one with the fewest breakdowns. It may be the one where breakdowns can be absorbed without turning the whole settlement brittle. Resilience is sometimes less about perfection than about graceful recovery. Repair tells us which route is closer to that standard. That may sound mundane, but mundane competence is exactly what separates survival theatre from real settlement. A place where people can diagnose, improvise, fabricate, and recover under pressure is a place beginning to trust itself. Until then, every broken component is also a psychological message. It reminds the crew that their world is still provisional and that confidence has not yet caught up with ambition. One reason planets keep their appeal, even after all the biological and environmental cautions, is that they provide a passive background no machine can fully imitate. Terrain remains terrain even when the power flickers. A cliff does not need active control to remain a cliff. Regolith does not vanish because one subsystem failed. A planet can still be deadly. Passive background is not passive safety. But there is a difference between living in the wrong natural environment and living in an environment that exists only as long as its integrated systems hold together. That difference sharpens the risk profile of an artificial world. The same settlement that may offer better gravity and better chosen shielding can also concentrate failure in unnerving ways. Pressure, rotation, structural integrity, atmosphere management, water recovery, food production, waste processing, power, thermal control and guidance can all belong to the same enclosed fabric. If several of those fail together, there is no tolerant outdoors waiting beyond the airlock. There is only vacuum and the structure itself. Control and fragility often arrive together. That is one of the hardest ideas in this whole documentary, because the mind likes to treat control as a synonym for safety. In ordinary life, they often overlap. In a habitat, more control can mean more dependency. The settlement may regulate light, climate, gravity and shielding more effectively than Mars can. It may also depend on more subsystems staying healthy at the same time. A habitat can feel like a town while remaining, in a deeper sense, a ship. That does not mean it is doomed. Ships can be designed well. Redundancy can be built in. Compartments can isolate failure. Rotation systems can be over-engineered. Structural monitoring can become routine. The point is not that a habitat must fail. The point is that its failure modes are concentrated and coupled. When things go badly enough, many parts of the environment are threatened at once because so much of the environment is built. Mars has its own ugly version of this. A buried base can lose pressure. Life support can fail. Radiation protection can be compromised by structural breach or bad siting. The difference is that some parts of the broader environment do not depend on the base continuing to function. Terrain still exists. Shielding mass still exists. The planet remains as matter, even when the colony has a catastrophic day. A habitat has to maintain far more of its world continuously, or the world disappears with the system. This is where the comparison gets sharper rather than simpler. Mars may be the wrong environment in several critical ways, while still providing passive physical background. A habitat may be the better-tuned environment, while also being the more systemically brittle one. Those are not small differences in flavor. They are different philosophies of survival. One asks people to endure the indifference of a planet. The other asks them to trust the discipline of a machine world they can never stop servicing. For some people, that contrast pushes them back toward Mars. Better a harsh planet than a giant device. For others, the body problem pulls them the other way. Better a device whose conditions can be tuned than a planet whose gravity and radiation cannot be negotiated with. The important thing is that the argument remains live this late in the film. No honest account gets to escape the trade, and if an artificial world remains a giant controlled system, then it needs something before it needs settlers. It needs an industry broad enough to build, feed, shield and repair the world at scale. Redundancy is the natural response to that fear, and it helps. Extra loops, backup volumes, compartmentalization, emergency stores, structural margin, and fault monitoring can all make a habitat more survivable. But redundancy is never free. It adds mass, complexity, inspection burden, and the risk that the backup system carries its own hidden weakness. The effort to harden a world machine can deepen the very industrial and maintenance load that makes world machines difficult in the first place. Mars makes a different offer. It does not promise graceful failure, but it does spread certain dependencies into the surrounding environment. There is ground beneath the structures, whether or not power is stable. There is local shielding mass, whether or not the next cargo mission launches on time. Those facts do not save a failing habitat on Mars by themselves. They do mean the colony leans on a larger piece of reality that was not built by the crew. The real contrast, then, is not between safe and unsafe. It is between diffuse and concentrated dependence. Mars diffuses some dependence into geology and site choice, while leaving huge biological and operational burdens in place. A habitat concentrates more of the entire settlement into designed systems, while gaining the power to tune the environment more deliberately. Neither condition is inherently superior. Each one changes what failure feels like. That is why the artificial world idea remains so tense all the way through. Its promise and its warning are the same thing. Humans would be living inside a place they made. If they make it well, the environment may fit them better than Mars does. If they make it badly, there is almost nowhere for the mistake to hide. There is a psychological side to concentrated failure as well. On Earth, people can often ignore the systems behind daily life because those systems are distributed across a huge planet-scale network. In a habitat, residents may know more clearly that the world around them is finite, enclosed, and contingent. That awareness could shape behavior, politics, design philosophy, and even the emotional tone of ordinary life. Some people may find that clarity grounding, others may find it exhausting. Mars offers a different psychological bargain. The outside world is plainly hostile, but it is also plainly there. A person can feel held by terrain even while knowing they cannot safely breathe it. A habitat offers closeness to the environment in another form. Everything that keeps you alive is near, inspectable, and in some sense human-made. The settlement question may therefore involve not only physiology and logistics, but which kind of dependence humans are better at living with. That should make us cautious about easy claims on behalf of either route. The right answer may vary across eras and across kinds of settlement. Early outposts might prefer one risk pattern. Later, larger communities might prefer another. What matters for now is that single-point fragility is not a footnote to artificial worlds. It is one of their defining prices. The same awareness may influence design choices from the first day. How much transparency is worth keeping? How much compartmentalization feels acceptable? How much redundancy can be afforded? How residents are taught to think about their environment. A world machine is not only built out of hardware, it is built out of attitudes toward risk, patience, and mutual obligation. That makes the single-point problem cultural as well as technical. Perhaps the cleanest way to say it is this: artificial worlds make responsibility visible. On a planet, some background conditions exist, whether or not a settlement is wise. In a habitat, more of the background has to be earned continuously. That can be empowering because it gives humans design control. It can also be merciless because design control means more of the blame belongs to us when the world fails to hold. For that reason, some future residents may prefer the blunt honesty of a world machine. The settlement announces its dependence instead of hiding it. Every system can be studied, improved, argued over, and redesigned. Mars may feel older and more grounded. A habitat may feel more accountable. Which of those conditions produces better long-term habitation remains part of the question rather than part of the answer. That burden of responsibility may be one reason early artificial worlds stay small and tightly supervised. Scale multiplies consequence. Until humans learn how to carry that consequence steadily, caution itself may become one of the main design features. The habitat case runs into its heaviest burden here because the full weight of industry comes back into view. A large rotating settlement is never only a habitat. It is also a supply chain. Structure, shielding, bearings or equivalent rotation hardware, pressure systems, power distribution, water recovery, atmosphere control, farms, replacement parts, tools, monitoring systems, and emergency reserves all have to come from somewhere. The settlement is a destination only after an upstream economy can keep it alive. That is why old design studies like NASA's space settlements work are so useful and so easy to misuse. They show that the concept can be treated as engineering rather than fantasy. They do not prove that the whole supporting civilization is near at hand. A cross-section can look complete long before the industrial web behind it exists. The more persuasive a habitat becomes biologically, the more punishing it can become industrially. Mars recovers its strongest late advantage right here. The planet is already in place, with ground, bulk mass, and usable terrain waiting in deep space before humans add a single pressure shell. If crews can reach Mars and establish power, processing, and excavation, they begin with a planet-sized piece of infrastructure they did not have to assemble in orbit. That does not solve the gravity problem or the radiation problem. It does remove one class of industrial precondition, which is why Mars can look less front-loaded than a giant habitat, even when it remains harsh to inhabit. This is where caution has to stay audible. We do not have enough basis to say orbital industry is already practically closer than the industrial base a Mars settlement would need. The habitat argument is strongest elsewhere, especially on the body's requirements and on controllability. If human health and long-duration environmental tuning set the rules, then a built world may eventually look more honest than a hostile planet. That is a different claim from saying the industrial route to such a world is already the easier one. In fact, the industrial burden may be the main reason habitats arrive differently from how people imagine them. The first meaningful artificial world may not begin as a glorious, fully autonomous cylinder with farmland, towns and parks ready on opening day. It may begin as a more limited, heavily supported settlement tied closely to cislunar infrastructure, lunar material processing, or some other upstream network that is itself still fragile. In other words, the built world may appear first as a dependent frontier system, not as a complete civilizational leap. That is not a weakness in the argument, it is part of the argument. Once we stop demanding a clean contest between Mars City and giant free space utopia, the timeline can become more believable. A smaller, supported habitat designed around controllable gravity and shielding may precede any truly self-sufficient colony, whether on Mars or in free space. The question then becomes which route reaches durable habitation first, not which route wins some perfect end-state race. There is a wider lesson here too. Space settlement debates often compare final forms: Mars civilization versus cylinder civilization, surface world versus artificial world. But real history often moves through awkward middle forms: ports before nations, stations before cities, depots before suburbs. If the body demands certain conditions that Mars cannot provide naturally, humans may build partial artificial worlds earlier than their imaginations once expected, even while remaining far from anything like a self-contained orbital society. That bounded possibility is enough to keep the habitat side alive without overstating it. The first built world may arrive slowly, remain dependent, and fall short of the grandest version of the word colony in its earliest form. But if it appears before a true Mars civilization, the reason will likely be straightforward. It would allow humans to control the conditions their bodies trust, even while forcing them to pay an enormous industrial price for that privilege. Which means the final question is no longer whether Mars or habitats win outright. It is what counts as the first serious off-world home. Industry here should be understood in the broadest sense. Not only factories, but transport, mining or extraction, processing, fabrication, inspection, storage, workforce training, and the political patience to maintain all of that before the visible prize fully exists. A large habitat asks for civilization upstream. The shell at the end of the process is only the part artists like to draw. This is why cislunar space appears in so many serious versions of the discussion. It is not because the moon or nearby space automatically solves the problem. It is because distance still matters. The closer the first artificial world is to Earth, the easier it is to move people, parts, oversight, and rescue relative to Mars. If a built world arrives first, there is a strong logic to the idea that it begins where logistics are least impossible, not where the final dream looks most complete. Mars, in contrast, can sometimes use distance to its own advantage conceptually. Once the transport burden is accepted, the colony arrives at a ready-made destination with local mass already waiting. That can make a Mars first strategy look more direct. Build the ships, reach the planet, grow from there. The habitat route may look less direct because so much invisible preparation has to succeed before the settlement itself can even appear in full. Yet directness can mislead. A route can be more direct to begin and more punishing to inhabit. The strongest reply is straightforward. If the body continues to reject low gravity and radiation-heavy environments, the supposedly more direct path may end in a harsher long-term compromise than the slower route that builds more of the environment by hand. There is no simple answer here. That is why the comparison has to stay conservative at this point. That civilization upstream would also need durability, not only brilliance. A burst of construction is not enough if replacement parts, shielding, feedstock, and maintenance capacity cannot be sustained across decades. Habitats reward continuity. They punish glamour without follow-through. The first serious built world may therefore depend less on one spectacular breakthrough than on many less dramatic industries becoming dependable together. This is where talk about destiny can become actively misleading. Mars is often treated as destiny because it is visible. Orbital habitats are sometimes treated as destiny because they seem to fit a technologically ambitious future. But destiny is not a planning category. Supply, fabrication, storage, workforce and repair are planning categories. Any route that cannot support those quietly brutal basics remains more like a vision than a home. The industrial burden is therefore not merely a reason to doubt habitats. It is also a filter that tells us what kind of habitats deserve to be discussed seriously. The believable ones are the ones embedded in a wider material system, not the ones floating free as perfect drawings. If the first artificial world arrives before Mars becomes a true colony, it will likely do so because that wider system finally became good enough to keep a smaller world alive. Seen that way, the first artificial world might be less like the opening of a grand city and more like the maturation of an ecosystem of support. Ore moved reliably, components fabricated reliably, crews trained reliably, repairs supplied reliably. The habitat at the end would simply be the visible tip of a much larger achievement. Humans learning how to hold a remote environment steady without pretending the hard parts are already behind them. That perspective helps explain why so many debates about settlement feel mismatched. One side is often talking about the destination image. The other is talking about the infrastructure required to make the image honest. Both are discussing the same place but at different scales of time. Habitats suffer badly when those scales are confused because their elegance at the destination end can hide just how much industrial patience is needed beforehand. The discipline here is to keep the habitat argument pointed at the right target. It does not have to prove that giant orbital construction is the next obvious step. It only has to show that if human health keeps demanding more control than Mars can give, then industry may eventually be asked to build that control somewhere closer to Earth first. That is a slower claim. It is also a much sturdier one. By the end of this comparison, the clean winner starts to dissolve. Mars still carries enormous appeal because it is a real world with local mass, buried ice, and a planetary stage ready to receive human machinery. A large habitat remains compelling for a different reason. It offers the chance to tune gravity, design shielding intentionally, and build around long-term human physiology instead of asking physiology to compromise with a hostile world. But neither path cleanly produces a self-sufficient civilization in the near term. That suggests a middle category may matter more than people expect. The first meaningful artificial world may be a frontier habitat in cislunar space, still rotating, still heavily shielded, and still strongly supported by Earth and nearby infrastructure. It would not be independent in the full cultural sense. Imported equipment would remain important, spare parts would still arrive from outside, and some food might as well. Yet such a place could still become colony-like if people live there for long spans under conditions designed for habitation rather than for mere transit. Why might such a place come first? Because the body may force the sequence. If low gravity remains unresolved, the incentive to create a more Earth-like baseline becomes stronger. If radiation remains a chronic threat, shielding geometry starts to matter more. If life support loops remain maintenance-heavy, the value of placing settlement where repair, oversight and resupply are at least somewhat more manageable also grows. A frontier habitat near Earth or the Moon could answer those combined pressures without pretending that the whole problem has been solved. That does not mean Mars disappears from the story. Mars could still host serious outposts, scientific bases, industrial footholds, even long-duration communities before free space hosts a truly autonomous habitat world. The point is narrower. The first place beyond Earth that begins to feel like a durable human home may not be the place that offered the strongest frontier romance. It may be the place where humans could tune the background conditions most carefully while accepting dependency and maintenance as the cost. There is something almost humbling in that conclusion. It suggests the real threshold for settlement is not courage in the old frontier sense, It is maturity. Can humans manage a world machine responsibly enough to live inside it for years? Can they maintain loops without lying to themselves about their fragility? Can they choose a habitat because it meets biological needs, not because it flatters technological ambition? Can they accept support and limitation before claiming the word colony too quickly? This is also where the Mars versus habitat rivalry starts to soften. They may not be rival dreams so much as rival bundles of compromise. Mars offers a natural world with costly biological deficits. A habitat offers a tunable world with costly industrial deficits. Depending on what problem humans solve first, one route may deliver the first durable home while the other remains a later ambition. The contest is real, but it is not a morality play, and that may be the most useful correction of all. The future beyond Earth is often narrated as if people must choose the noble planet or the artificial machine. In practice, the first serious off-world home may arrive where the compromise package is least destructive, not where the imagery is most stirring. A supported artificial world could meet that definition before Mars does. A Mars settlement could still outrun it if industrial build-out near Earth stalls and planetary resource use advances faster. The honest answer remains bounded because the evidence remains bounded. What we can say is this: the body has a vote, gravity has a vote, radiation has a vote, water, air, agriculture, repair and industry all have votes. A serious home beyond Earth will appear where those votes can be gathered into a survivable system before they can be gathered somewhere else. That system may look less like a city on a planet and more like a carefully managed world under construction. The word outpost helps because it lowers the temperature without lowering the seriousness. An outpost can be durable, inhabited for long spans, socially meaningful, and technically advanced without pretending that it has solved every upstream dependency. Human history is full of places that mattered deeply before they became self-sustaining in any romantic sense. Space settlement may need the same humility. A supported rotating habitat near Earth or the Moon could fit that pattern. For years it might still depend on imported supplies and on Earth for medicine, specialized components, or much of its food. Even so, it could count as a major step if people remain there under gravity they chose, with shielding they arranged, inside loops robust enough that departure becomes optional except in emergency. That would already be a very different category from a transit vehicle or temporary station, and it would matter even before full autonomy arrived. Mars can produce its own middle forms as well. Scientific bases could grow into industrial footholds. Protected living volumes could expand into communities that are still far from independent, but no longer feel like brief expeditions. The future may therefore contain several partial settlements before it contains one unquestioned colony. That possibility should make us suspicious of clean headlines and grand declarations. What survives this uncertainty is the main pressure of the film. A serious off-world home will emerge where the package of compromise becomes livable first. That place may begin smaller than many people want and more dependent than many people hoped. Yet it could still count as the first artificial world that matters if it proves that humans can rebuild a trustworthy background for life away from Earth. That is why the word first matters so much. First does not mean final. The first serious artificial world could be modest relative to later visions and still reshape the whole discussion. Once humans demonstrate that a designed environment with chosen gravity, chosen shielding and robust loops can host long-duration life, the emotional monopoly of planets may weaken. The mind may start accepting that homes beyond Earth do not have to begin on natural surfaces. The same could happen in reverse if Mars manages durable habitation first under conditions that keep residents healthy enough and systems stable enough. Then the planet would regain its claim as the more direct route. Either outcome would teach the same lesson. Settlement is decided less by slogans than by which package of compromises finally works in practice. So the middle ground is not a way of dodging the question, it may be the most realistic answer available while evidence is still incomplete. Outposts, supported habitats, and expanding protected communities could all matter before anyone deserves to say that humanity has founded a fully autonomous second world. This is not a forecast disguised as certainty. We do not know which route will prove itself first. What we do know is what kind of evidence would matter when the time comes. Not only launch success and first footprints, but years of healthy habitation, stable loops, repair competence, and the slow disappearance of emergency posture from daily life. The first world that achieves that will have crossed the line this film has been tracing. And once a supported habitat or supported Mars community proves durable enough, the vocabulary may shift very quickly. What seemed temporary can become ordinary through repetition. Children born into the system, workers planning years instead of months, and institutions built around maintenance rather than mission milestones would all signal that something more than presence has begun. The first colony may therefore arrive by looking less dramatic than many people expected. That may be the right level of humility for the whole subject. Human expansion beyond Earth will probably not begin with clean categories and final forms. It will begin with supported places that gradually prove whether they deserve stronger names. An artificial world that is still dependent can matter. A Mars settlement that is still incomplete can matter. The first serious home will not be the one with the best slogan. It will be the one that quietly keeps working. If that sounds less triumphant than some visions of settlement, it may also be more durable. Real second worlds will probably begin with careful systems, narrow margins, and habits of maintenance that feel closer to stewardship than conquest. That is enough. A serious home beyond Earth does not need to flatter our myths. It only needs to keep people alive well enough, long enough, and honestly enough that the place stops feeling borrowed. At the start, Mars looked honest because it was already there. A red horizon, real ground, a destination that seemed to save us from having to invent too much. The rotating habitat looked strange by comparison, almost theatrical. A world that admits it is a machine. By now the contrast has changed. Mars still carries the dignity of a real planet. But a real planet can still give the human body the wrong baseline. It can still force people into buried habitats, heavy shielding, incomplete life support loops, and years inside machinery that only borrow the comfort of an open sky in imagination. A built world still carries the burden of fabrication, rotation, maintenance, and mass. But that same burden lets humans ask for gravity closer to what their bodies trust, shielding placed where they need it, and an environment tuned on purpose rather than accepted on faith. That does not make the artificial world easy. It may remain the harder industrial project for a long time. It may arrive first only in a smaller, supported form. Mars stays in the race precisely because nature already put a world there, waiting with local material even if its conditions are harsh. So the likely answer is not that giant orbital civilization is simple, or that Mars is a mistake. It is that the first serious human home beyond Earth may appear where humans can rebuild the hidden Earth conditions most carefully before they can fully tame a hostile planet. The first world may be built before it is found. And if that happens, the most natural-looking choice will not have lost because it lacked beauty or scale. It will have lost, for a while, because the body asked for a different kind of honesty. There is a kind of poetic justice in that possibility. The place that once seemed most artificial may turn out to be the place that takes human biological reality most seriously. The place that once seemed most natural may turn out to demand the harsher bargain. Not because Mars failed to be beautiful, but because beauty was never the deciding variable. So the final image to keep is not Mars against a machine in the simple sense. It is two different answers to the same human demand. One says, go to a real world and endure what it gives you. The other says, build a smaller world and carry the burden of making it work. The first serious home beyond Earth may belong to whichever answer humans can sustain with the least damaging lie. Perhaps that is the best way to leave the question, not with a winner declared too early, but with the standard clarified. The first true step beyond Earth will not be the first dramatic arrival. It will be the first place where people can remain, stay healthy enough, repair what fails, and trust the environment around them without constant denial. If that standard favors a built world before it favors Mars, then the built world will have earned the title honestly. That is why the comparison should stay conservative even at the end. Habitats may fit the body better and still lag in industry. Mars may lag in biology and still lead in directness. The tension between those truths is not a flaw in the story, it is the story. Humans are trying to decide whether the first real home beyond Earth should be discovered inside a planet's limits, or assembled piece by piece around the conditions a body can actually endure. In that sense, the first built world would not be a rejection of planets. It would be a confession about what humans need from a home. We may reach Mars early, we may work on Mars early, but the first place that fully starts to trust human bodies may be the place where gravity, shielding, air, water, and repair were designed together instead of inherited separately from a beautiful but harsher world.